Let's do an example with looking at combinations and permutations. We're going to try these two short problems. Suppose that a committee of 3 people are to be selected from a group of 6 people. How many choices are possible? Well, okay. First of all, I think, does order matter of how people are chosen? And the answer is no, order doesn't matter because we're looking at a committee and there's no indication that there would be a ranking of the members. So if I'm thinking about combinations, makes me think of combinations, and you're like, well, why would I think of combinations? And I thought, oh, I went back here and I see order does not matter. I'm going to use combinations. So in this case, I'm going to do 6 choose 3, which gives me 6 factorial over 6 minus 3 factorial times 3 factorial. Remember, this 3 factorial right here gets rid of any duplicates. You notice I'm not writing out the full sample space. I don't need to. So then I have 6 times 5, and I'm just going to write it out here. And this will be 3 factorial. And this will also be 3 factorial. 6 minus 3 is 3. Now, can I reduce this? Sure. And I end up with 20. Now, in the next part, suppose that a president, secretary, and treasurer are to be selected from a group of 6 people. How many choices are there? Well, in this case, I think, does order matter? And I think, yeah, it does. Order does matter. We're going to elect a president. Once I've elected a president, there are less people, fewer people that I can choose then for the other positions. So order matters. This is a permutation. I'm going to show it both ways. I'm going to show it using this formula and also using it just thinking about, for simple problems like this, you can think, well, the first person, I have 6 people. I'm going to, let's say, elect the president first. Now, when I go to elect the secretary, there are only 5 left. And then finally, for the treasurer, there are 4. You're going to notice here, that the number is quite a bit larger than the number of combinations. And that makes sense. We're getting rid of, and you're like, well, 120 divided by 20 is 6. Yes, that is actually 3 factorial. So it's getting rid of our duplicates. Could I do it the way with using the formula? Certainly. 6 factorial over 6 minus 3 factorial is going to give me that 6 times 5 times 4 times 3 times 2 times 1 all over 3 times 2 times 1, and I get 120. So for simple problems like this, you could do it either way. But as problems get more challenging, it can be very useful to use the formulas. Let's finish up this section with an example. At a local university, suppose a committee of 2 people is chosen from 4 faculty and 2 students. Now, first, how many ways are there to choose the committee? First, calculate the value, then write out all the possibilities. Well, we know, first of all, I'm going to label the faculty as A, B, C, D. And the students, to make it clear, I'm going to call them 1 and 2. And that way it'll be easy for us to pick out the arrangements with faculty versus students. How many ways are there to choose a committee? Well, does order matter? And you're like, well, we've talked about committees before. Order doesn't matter. No, so you could do, in this case, I've got choose a committee and the committee of 2 people. So there'll be 1 out of the 6 total. So there's 6 total people that can be chosen from the 4 plus the 2. And then once you choose 1 person, there are 5 left and you get 30. Now, does order matter? No, order does not matter in this case. So let's check ourselves. Order does not matter. So I know if order doesn't matter, I can do 6, choose 2. So then I'll end up with 6 factorial over 6 minus 2 factorial times 2 factorial, and then it gets to be 15. You're like, oh, wait a minute. This is one of those times I did this specifically incorrectly. I wanted everyone to start thinking about, okay, if I can check myself a lot of times with these formulas. This method assumes order matters. Okay, so this is assuming order matters. So that is the number of permutations. We're interested in the combinations though. So be very careful as you use these. It's tempting to say, well, I'll just do this method. Nope, it doesn't work. This is wrong in this case because order does not matter. All right, so we need to take out those duplicates. Let's check ourselves and make sure that, oh, we are really getting this. Let's write out the sample space and see if we really do we get 30 or do we get 15? Alrighty. So we know that AB is going to be the same as BA. So we don't need to duplicate those. We only need to write one of the two of them. And that should already give me the clue that this is actually the correct one. So if you were yelling in your head, ooh, this doesn't seem right, you were 100% right. So let's see, I'm going to start with A, and A can go with B. Let's do everything with A first. A can go with C, A, D, and then each with the students. Now you may be like, well, I'm going to do the next thing with, I'm going to start with B, no, and do BA. No, remember, we're looking at a committee. Order does not matter. So we've taken care of all the A's that can happen, all the committees with A. So now let's think about, okay, taking care of that, let's do B. So I'm going to get BC, BD, B1, and B2. Have I taken care of all of the committees that could have person B in it? Yes. Pause, take a moment, and see if you can complete the rest of this sample space. So hopefully you paused and you saw that you came up with this. If you count it out, you get 15, which is what we got here. How many ways are there to choose a subgroup containing 2 students? And what's that combination? Well, we only see one way. Okay, there's just one way, and that combination is 1, 2 right here. Could I do that with choosing, could I use the combinations where order doesn't matter? Yes. Remember, we're choosing a committee of 2. How many students are there possible? Well, there are 2 students possible. So out of 2, we're going to choose both of them. 2 factorial over 2 minus 2 factorial times 2 factorial. Remember, this is 0 factorial, which is 1. So I end up with 2 factorial over 2 factorial, which is just 1. So I got the same answer. If a committee is selected at random, what's the probability that it contains 2 students? So probability of 2 students. We know the total number of possible outcomes is 15. And there's only one arrangement that has exactly 2 students. You could also do it as, alrighty, we know we're going to do 6 choose 2, and that gives us how many different committees can be chosen. And on top, we can do the 2 choose 2 because we're going to choose the 2 students, and you'll end up with the same number. Now, this method I go over because students have frequently done this in another probability or statistics course or statistics course. So I like to show that calculation, but either way it works. Now, if a committee is chosen at random, what's the probability it contains 1 faculty member and 1 student? Well, we have to count out the number of times. First of all, there are 15 possible outcomes. And we're interested, our outcome of interest, the event of interest, is when there's 1 student and 1 faculty member. And that is right here. And there are 8 total. And you get 0.533. Could I have done it the longer way? Yeah, or you could do it this way. Especially if you've done more probability, this may be more comfortable for you. You know, out of 6 people total, you're going to choose 2. Out of the 4 faculty, we're going to choose 1, and out of the 2 students, we're going to choose 1 student. And if you do this, you'll end up with 8 divided by 15, the exact same answer. Now, counting can get really, really ugly really quickly. it can get complicated. The numbers can get very large very quickly. So in this class, we're not going to spend a ton of time on counting, but it is necessary to help us with these probability problems and down the road with statistics.